Section 9.5 is about what are called power series. Power series are they are infinite sums where the terms are powers of x. That's why it's called a power series. In chapter 10, we're going to learn about a special kind of power series called a Taylor series. And I'd like to motivate power series by considering a Taylor series, actually. So this is a little preview of chapter 10, but its purpose is to illustrate ideas at the end of chapter 9. I'm going to consider the function f of x equals 4 over 9 plus 25x squared. And I'm wondering, can I write this as an infinite sum? A power series, most typically written as, say, c sub 0, which is a constant, plus c1 times x plus c2 times x squared plus c3 times x cubed, etc. These c's are coefficients of powers of x. Can I do this? I'll put a question mark there. The answer is yes. And I'm going to show you how to do it. It's a bit tricky, but I think kind of fun. I'm going to use something I already know, that you already know, the formula for a geometric series that converges. I'm using an r here instead of an x. We know this converges to an a over 1 minus r. If what? If the absolute value of r is less than 1. We know this. This is something you should remember for the rest of your life, okay? I'm serious. I'm semi-serious about that, okay? Maybe, I won't hold you to it, but I'm semi-serious that you should remember these kinds of things for the rest of your life as best you can. They are culturally significant, you might say. The absolute value of r being less than 1 means r itself is between -1 and 1. Always remember that equivalence. That helps you understand this better. How can I possibly use this, though? So far, when we've used this formula, we've had an infinite series, and we wanted to simplify it to that. This time, however, we're going to go in reverse. We're going to start with something like that and write it as a series. We're going to try to write that thing as a series. However, we seem to be hitting a snag here, maybe a couple snags, in trying to use this formula, it seems. One snag is that there's a plus sign there instead of a minus sign. Oh, that's pretty easy to fix. Adding something is the same as subtracting a negative. Another snag is that we have a 9 there instead of a 1. That's pretty easy to fix too, because you can just factor out the 9 out of the bottom like this. Careful, you're going to have 25x squared over 9 there. And then dividing by the 9 there is the same as having a 4/9 in the numerator. And let me go ahead and write this plus sign now as a minus of a minus. And I now see that these two things, they match their form if a is 4/9 and r is -25x squared over 9. Yes, it's a complicated r, but there's just symbols representing numbers. Why not? So if this is true, what's in red here, I should be able to use it going backwards from right to left with that value of a and that value of r. So it's going to give me a 4/9 plus a times r, 4/9 times -25x squared over 9. plus a times r cubed plus a time or squared, I mean squared plus a times r cubed, etc. plus dot dot dots. Don't forget the plus dot dot dots. It's essential that they're there. That is a way to write this function as an infinite series. Now, it begs the question, why would you ever do such a thing? There are some good reasons for it. One example I'll hint at is that writing it as an infinite sum actually sometimes helps you approximate the integral of the function nicely. Now, you don't really need to for this function because you can relate the integral of this to arctangent, inverse tangent fairly easily with some tricks. So you don't really need to do it for this example. But there are some examples where you can't really relate. You can't do the integral in the ordinary way. And so you have to approximate the integral either using like Simpson's rule or using an infinite sum and approximating it by truncating it somewhere. That's an example of an application of this kind of thing. Now we could simplify this, and I think I will just for the sake of doing it. This will simplify to 4/9 minus, let's see, 25 times 4 is 100. 9 times 9 is 81. I get an x squared is the lowest power of x, except for the constant term. Not an x. In other words, the C1 is going to be 0. There's no x term. In fact, there's going to be no odd degree terms in all this because I'll be multiplying those exponents. The C3 will be 0, the C5 will be 0, etc. It's the even powered terms that have non-zero C's. Let me go ahead and simplify the other ones. Negative 25 squared is positive 625 multiplied by 4. Let's see, 625 times 2 is 1250 times 2 again is 2500 over 9 cubed, which is 729, right? Yeah. X to the 4th. Multiply the exponents there, 2 times 2. Just gonna double check things here. So 625 is negative 25 squared times 4. Yep, that's 2500. 9 cubed, 729. Let's go ahead and do the one more. That'll be a negative sign because it's to an odd power with this negative sign here. 25 cubed is 15,625 times 4 is 62,500. We'll be dividing by 9 to the 4th power, 6,561. X to the 6th power, you'd multiply 2 times 3, etc. plus dot dot dots. What's my purpose in this? Well, I have multiple purposes. One thing is to illustrate that this can be used in reverse. Another purpose is to then use it and get something in this form, which I will ultimately apply the ratio test to figure out the values of x for which it converges. To simplify it, to show you how Mathematica can check our answer, it's a built-in function called series. I'm going to write this down. Type the function 4 over 9 plus 25x squared. Put a comma. Then in a list, put x, comma, 0, comma. To see at least through the 6th power, I better put a 7 there. Series. What's the 0 for? The 0 corresponds to the fact that this series is said to be centered on 0, and there's a couple ways to see that. One is that these powers of x could be thought of as powers of x minus 0. Another way to see that the series is centered on 0 is that it's going to turn out it will converge for values of x in an interval centered on 0. Anyway, let's just see that this gives the same answer. Yep. Look at those fractions. 4/9, -100/81, etc. Those are all the same. Pretty amazing, huh? You know, it is plus dot, dot, dots. Mathematica doesn't write plus dot, dot, dots. Instead, it writes, what is that? 0 times x to the 8th? What is that? It's not a 0. It's an O. In fact, it's a big O, as in big O notation, if you've ever heard of that. Computer science kind of topic. It's saying effectively there are higher order terms with x to the 8th power and higher that are missing, not being shown. They do exist, however, and the functions are not equal unless you include all the terms going on forever. But with Mathematica, we can go on a long ways and see lots and lots of terms. Maybe even, you know. Oh, okay. It did it. I meant to do 51, but I did 251 there. Look at that. Those are humongous fractions. I'll go back to 51. We're through x to the 50th power. Okay, plus higher order terms. Okay, and again, they're only equal if you go out forever. They're really good approximations if you stop somewhere, if you truncate. All right, so we've done it right. What about the interval of convergence, it's called? For what values of x is this valid? We get equality there if what? If the absolute value of r is less than 1, just like up here. But what's r? It's -25x²/9. That's what's got to be less than 1. Yeah. Simplify it. You can bring the -25/9 out in front as a positive 25/9 because of the absolute value signs. And then the absolute value of x² is the same as the absolute value of x quantity squared. We actually can get rid of the absolute value signs here because the power of x is even. However, if we had done an example where the power of x was odd, we could not do that. So let's just keep the absolute value signs there. Divide both sides by 25/9, same as multiplying by 9/25. And then, square. Then take the square root of both sides. And the absolute value of x is not negative, so I can just write this like this. The absolute value of x needs to be less than 3/5, which is 0.6. In other words, x itself must be between -0.6 and +0.6. That's based on the geometric series formula. That's based on knowledge of geometric series. And I know it's going to diverge otherwise. In other words, the values of x where this converges is an interval centered at 0, going between -0.6 and +0.6, not including the endpoints. It's an open interval of convergence. Next week, we're going to have a little bit of fun. Not going to test you on it, but we're going to have a little bit of fun talking about complex numbers a little bit. All these calculations that I just did are still valid if x is a complex number. A plus bi, where I² is -1. Instead of an interval of convergence on a real number line, what you get when you consider x to be a complex number is a disk of convergence in what's called the complex plane, where you have a real axis going horizontal and a so-called imaginary axis going vertical. But you do draw it, even though we call it an imaginary axis, we still draw it. We really do draw it real. It's real. It becomes a disk of convergence. Everything inside this disk are going to be complex numbers where the series converges. And the disk is the inside of a circle, and the circle's got a radius, r. And this is called the radius of convergence. But we still call it a radius of convergence for the interval, even if we don't think about complex numbers. If you kind of pretend the interval is a degenerate circle centered at 0, what's the radius? Not diameter, but radius. 0.6. And yes, because this is a geometric series, it does not converge at the endpoints or when you're outside the interval. I didn't really make this open circle here big enough. The interval of convergence is an open interval. But there are some examples where the interval of convergence is not an open interval. You include both endpoints or maybe just one endpoint. And with complex numbers, when you would get a disk of convergence, sometimes you might still include points along the boundary circle as part of the disk of convergence. It gets tricky. What we want to do in the time we have left is first confirm this interval of convergence using a different method, the ratio test. You have to do this in section 9.5. And secondly, do one more example. To confirm the interval of convergence using the ratio test, it's best to use the unsimplified formula right here. Let's do that. Let me rewrite it. 4/9 plus 4/9 times negative 25x squared over 9 plus 4/9 times negative 25x squared over 9 squared plus 4/9 times negative 25x squared over 9 cubed, etc. Don't forget the plus dot dot dots. This can be written in summation notation, where you're adding up terms of the form 4/9 times negative 25x squared over 9 to higher and higher powers. We can either start the summation at 1 and make this first power an n minus 1, or what's more typically done in this context is start the summation at 0 and make this an n. Still an infinite sum. You can write it either way. You catch what I said? I could have started at 1. And if I do start at 1, I make that an n minus 1. Either way you do it, the first term is 4/9 because when n is 0, something to the 0 power is 1. Actually, it's a little bit of a lie. 0 to the 0 power is undefined, but let's not go there. This is now my an. Back to standard notation for an, not the notation with the alternating series test. Let's apply the ratio test. What does this ratio of absolute values equal? Okay, with the 1 on top, replace the n with n plus 1. On the bottom, it stays as an n. The negative sign could be factored out, so to speak. I could, for example, think of this thing as, if I wanted to, negative 1 to the n times 25x squared over 9 to the n. And apply that there, and ultimately get rid of the negative signs and also get rid of the absolute values. And it's actually probably a little bit easier in terms of simplification if I don't divide the fractions by multiplying by the reciprocal in this example, because you get cancellation right away here. So you don't have to bother writing it in terms of multiplying by the reciprocal. The 4/9 cancel completely, and these things cancel completely. Oh, I should keep my absolute value signs around the x squared in general, though. In the end, this equals 25/9 times the absolute value of x squared. That should look familiar. I wrote that down, what, 7-8 minutes ago? Right there. for the ratio test to guarantee convergence, and by the way, this doesn't depend on n, so it approaches itself as n goes to infinity. In general, you get something that does depend on n. For the ratio test to guarantee convergence, you want this to be less than 1. And just like before, that is equivalent to x being between negative 0.6 and positive 0.6. And that, again, is the interval of convergence for this example. However, it's a little bit tricky. When you apply the ratio test for examples like this in general, remember, if the limit of the ratios is equal to 1, the series might converge, it might diverge. The ratio test gives you no information. So while this is the interval of convergence for this geometric series example, we know it's an open interval not containing the endpoints. There are examples that do contain the endpoints in the interval of convergence.